This is Jane. Jane commutes to work every day and is a very safe driver, but today there was another driver on the road that was not so safe. Flash forward 2 weeks. Jane is completely recovered from her injuries. However, since the crash, she hasn't been able to get into a car without having intense feelings of panic, which has been interfering with her ability to get to work on time. A friend noticed these symptoms and pointed out that a nearby university was running an experiment about PTSD and motor vehicle trauma during which they would scan her brain using a thing called an fMRI. She would be shown some images and her brain's reaction would be recorded. So, what is an fMRI, and how could it help Jane understand more about her emotional trauma from the car accident?
An fMRI, or functional magnetic resonance imaging, is a method of diagnosing brain activity by monitoring circulation of blood through different parts of the brain. As opposed to a regular MRI, which just creates images of soft tissue, functional MRI allows for experimenters to see how the brain reacts to the presentation of different stimuli. The readings of an fMRI machine are sourced from hydrogen atoms found in high quantities in the blood that circulates through the brain. Interestingly, as the electron circles the hydrogen atom, the moving charge makes hydrogen act like a tiny magnet. A magnet is an object that creates a magnetic field. A magnetic field is a region around a magnetic material that is created by moving charges within the magnet. This tiny magnet is also known as a magnetic dipole. When a magnetic dipole mu is placed in a magnetic field B, it experiences a torque, tau, or a force that causes the dipole to rotate and align itself within the field. This principle is central to how MRI machines function. Chapter 38 in the Wolfson textbook, Nuclear Physics, provides the graphic you see here. A magnetic field, created by superconducting coils in the scanner, is applied to the patient's brain. Because there are magnetic dipoles mu, the hydrogen atoms in the blood experience a torque and align themselves with a magnetic field B. Then, a certain radio frequency, 64 megahertz to be exact, is applied by the scanner's field-modifying coil perpendicular to the magnetic field.
The absorption of the radio frequency's photons causes the hydrogen atoms in the blood to jump to a higher energy state and then drop back, emitting energy until they eventually return to equilibrium. The MRI scanner's receiver coil measures the summation of this emitted energy and how it is dispersed across different areas of the brain. This can inform the clinician about patterns of brain activity. After signing some consent forms, it is time for Jane to get in the scanner.
Suddenly, it all comes flooding back. The fear for her life, the claustrophobia she felt after the crash. She was terrified. But she also knew that if she wanted to know what was going on in her brain, she had to finish the study. So she buckled down, took some deep breaths, and pressed on. After 15 minutes of being shown images and responding to them, she was done.
Compared to healthy control subjects, she experienced higher brain activation in regions associated with stress after being shown the images of car crashes. These regions are known to be highly activated in subjects with post-traumatic stress disorder, or PTSD. So it was as Jane thought. She felt relieved to know that the fear she was experiencing was real. Afterward, she was paid for her time, and the doctor was able to recommend a therapist to help her with her symptoms. And for the first time since her crash, Jane felt optimistic again, and all thanks to the physics of functional magnetic resonance imaging.